Hello and welcome to this addendum about the Hodge star. I thought I'd do this since the definition I gave in the lecture about the de Rham complex, the definition of the Hodge star seemed sort of ad hoc and very weird. And there is actually a more or less coordinate-free way to define it. And this is what I'm going to look at now. And before we start, or before we get to the Hodge star, we need to talk a bit about oriented manifolds first. So that M be an n-dimensional manifold an orientation is a nowhere vanishing n-form. Notice that those are the same n, so we're looking at a form of the maximal degree, and it's global, and it has to be nowhere vanishing. Yeah, examples include like spheres, R2, Rn, whatever you want to think of, but not things like the Möbius strip or the Klein bottle or stuff like that, or projective space. And I guess some projective space, not all of them. And now an oriented manifold is a tuple M omega, where M is a manifold, and omega is an orientation. So not only does there exist an orientation, we have also explicitly picked one. And well, now we want to say something about the orientation of charts, and especially distinguish between positively and negatively oriented charts. So let M omega be an oriented manifold. The chart x1 till xn is called positively oriented. If there exists a positive function, so a chart open set U where we have the coordinates x1 until xn, if there exists a positive function such that dx1 wedge and so on dxn is equal to f times our orientation. Now, such a function always exists. It's always non-negative. And well, if we assume the chart to be connected, such a function exists, it's always non-zero. And if we choose our chart to be connected, it is either positive or negative. And if it's positive, we call the chart positively oriented. And otherwise, we call it negatively oriented. Or I guess if f is less than 0, the chart is called negatively oriented. And well, now we're going to define sort of for an oriented manifold a very concrete orientation. Or let's say, given an oriented Riemannian manifold, we're going to define a very concrete n-form on that has a very special name and properties and whatnot. So let mg small omega be pseudo-Riemannian and oriented. And then we define on a chart omega to be plus or minus square root of the absolute value of the determinant of the matrix whose ijth value or entry is given by G applied to the ith unit vector and the jth unit vector. So in GR, this thing is usually written as just the square root of the absolute value of G, where G is, well, exactly that determinant, but I've written it out, times dx1 wedge and so on dxn. Now, why the plus minus? Well, we take plus if the chart is positively oriented. And minus otherwise, or I guess if negatively oriented. Now I guess we want to somehow have an intuition why this is well defined, why it should be equal across charts, or I guess why it should be equal if you do a coordinate transformation. And the reason is that each of the dx1s, or each of the dxi, transforms with a factor of the Jacobian. Oh, I guess, yeah, I think it's the Jacobian, maybe. So then an n times alternating product transforms like the determinant of the Jacobian. And the matrix that we're taking the determinant here transforms like conjugated by the inverse of the Jacobian. Or not conjugated, but like the transpose, I think here. Well, anyway, so the determinant inside here transforms with a factor of the negative second power of the determinant of the Jacobian. So then when we take the square root, we get the absolute value of the determinant of the Jacobian. So overall, this whole thing transforms with the sign of the determinant of the Jacobian, or put differently, it transforms like +1 if we preserve orientation, or like -1 if we change orientation of the chart. And ta-da, this factor of plus or -1 transforms the same way. So in either case, it stays the same. Okay, so what's the big deal about this capital omega? This thing is called the Riemannian volume form. And it is what you usually use to integrate functions. Remember when in GR we sort of derived that now that we're working over manifolds, you have to include this square root of the determinant of the metric factor. Well, that's exactly this. because as we've seen in the lecture about the de Rham complex, the only thing you can integrate over a manifold, over an n-dimensional manifold or an n-chain, is an n form. But functions aren't n forms, they are zero forms. So we have to find some, or there has to be some canonical way of identifying the two. And this is via this capital omega. So the canonical way of integrating functions over an oriented Riemannian manifold is by integrating f times capital omega. And I guess in GR, generally in physics, this is just done automatically. And using this Riemannian volume form, we can define something else, but I guess there is something to prove, so this isn't strictly a definition, but lemma/definition. So again, let mg omega be oriented and pseudo-Riemannian. We define the dual pairing, which I will call scalar product, between omega k and omega k to C infinity m. And it's given by sending a wedge of k many one forms and another wedge of k many one forms to the determinant of the matrix whose ijth entry consists of the scalar product of the ith term and the jth term of the respective things. Now, what is G inverse? Well, again, in GR, there's a much easier notation, I guess, for this, because G induces an inner product on vector fields, but then it also identifies vector fields with one forms, and then you can also induce an inner product on one forms just by saying that, well, a tuple of one forms is mapped to one of the one form applied to, well, what if we turn one of the one forms again into a vector field, where phi from vector fields to one forms is just the map that sends a vector field to G of x and leaving the second thing free. So I guess this would be index lowering, and then phi inverse is index raising. Yeah, delta is a one form, so then phi inverse of delta is a vector field, and you can plug that into the other one form, and you thus get, well, not an inner product, but like a non-degenerate bilinear form, because generically G is not an inner product, but like can have negative, can be, sorry. Since we're dealing with a pseudo-Riemannian manifold, it doesn't have to be positive definite, that's all. And okay, that's a nice definition. What is the lemma part? Then this bracket defines an inner product, or I guess a degenerate bilinear form. Non-degenerate. On the C infinity M module, omega k. Notice that k can be any integer between 0 and n. And the fact that this is indeed an inner product means that we get some Riemannian type result, but I'm going to talk about this a bit later, or I guess I'm going to talk about this right now after I've shortly mentioned something about the proof. Since we're dealing with finite dimensional manifolds here, we can look at all of this locally, and then we're dealing with finite dimensional vector spaces. So this result just follows from linear algebra 2, or whenever you've done scalar products. So the proof doesn't require that much tooling, and you don't get in trouble because we don't have a Hilbert space or something. And well, now comes the big construction where we try to construct the Hodge star. As I've said, we have a Ries-Fréchet type result. If we have a linear form, so we have a C infinity M linear map from omega k to C infinity M. Then there is a unique beta in omega k such that for all alpha in omega k, this map is generated by just taking the scalar product with beta. And this is just because locally we're dealing with finite dimensional stuff, so everything just works. And now we take so ultimately we want to define the Hodge star using this result here. So we have to somehow construct a map from omega k to C infinity. And which map is this going to be? Well, essentially it's going to be the wedge product with another element. So let beta be an n minus k form. Then we have the map that takes the wedge product with beta, that takes a k form and produces an n form just by mapping alpha to alpha wedge beta. This is C linear, C infinity linear. Okay. Now, since our manifold is oriented, we have a very nice property, namely that omega n is generated, or like every element of every n form can be written as a multiple of capital omega. So we can sort of go on and map this one to C infinity just by saying that f times capital omega is mapped to f, where f is unique because it's oriented. So if we look at it now, we have, again, of course, this is also C infinity linear. We now have a map from omega k to C infinity, that is C infinity m, that is C infinity m linear. So we are exactly in this case here. So this map is induced by an element of omega k. And Well, I would like to say that this is the Hodge star, but it's actually the inverse of the Hodge star of beta. What does this mean? In other words, if now beta is a K-form, then star beta is the unique element of the unique K-form, such that for all other K-forms, we have alpha wedge star beta is equal to the inner product of alpha and beta. And well, this inner product is a scalar function. And here we have a K form and an n minus K form. So we have an n form, well, times capital omega. And I guess we can do one small example, namely K is equal to 0. Then we take, for example, beta is equal to 1. And then if alpha is another 0 form, i.e. a function, we have alpha wedge star 1 is equal to the inner product of alpha and 1 times omega. Now, since this is a 0 form and this is an n form, this is just the product. And since those are 0 forms, this is also just the product, which means that alpha times star 1 is alpha times omega, or star 1 is omega. And I guess this is not really a scalar product that we've defined because it doesn't map to a field, doesn't map to the basis field. Could view it in terms of the ring C infinity M, but maybe you still want to talk about sort of real inner products. For example, if you want to do functional analysis on manifolds, which I suppose is a very interesting problem, very interesting thing, then you might still want to define some kind of scalar product. And well, what can you do? We have somehow made this into n forms. And what can you do with n forms? You can integrate them. So define, well, now we have to use some different symbol. I chose double bracket for no particular reason. We can just define this to be the integral over the manifold M of, well, I guess either side of the equation above. Where, very importantly, we have an oriented manifold, so there is a notion of integrating over that manifold, not just over chains, just by choosing charts that are all have the same orientation, choosing a partition of unity subordinate to that cover, pulling back along the charts. Well, yeah, it is possible. It's just a bit uglier than integration over chains. And more importantly, we have to take care that this integral is actually finite and also well defined. I mean, could have infinitely large positive and negative parts too. So for alpha and beta, in the set where that integral is indeed defined, I guess we would like G to actually be a scalar product now, so maybe it would be nice to just consider the Riemannian case. For alpha and beta in the set of K forms where I guess you could say alpha wedge star alpha is integrable, which just means that that integral for alpha and alpha exists and is finite. And well, we then have an R vector space with an inner product, and then we can take the completion of that pre-Hilbert of that inner product space with respect to the scalar product, and then we can get a Hilbert space. And I guess you could call it omega k L2 of M, which doesn't have, or whose elements are not smooth functions anymore, or anything smooth. So this is a whole lot bigger, a whole lot more ugly, but it is a Hilbert space. Of differential forms, and you can do functional analysis on that. And that was really all I wanted to say.